In this video, I would like to expand the histogram filter to more dimensions. In the last section, we saw that a one-dimensional histogram filter splits the domain into different bins or buckets. If you want to refine the resolution, you must take smaller bins, which basically means to add more bins. We can compute the probability of each bin, and from that, to draw the PDF or the posterior probability density function. Again, if we want to be more accurate, we must add bins. But, and this is important, the histogram filter's complexity is exponential. What do I mean by that? Let's say that the domain is 20 meters long and I have 20 bins. It means that my 1D resolution will be 1 meter, or 1 bin for each meter. When I add another dimension from 1D to 2D, if I want to keep the accuracy, I will need 20 bins for the x-axis times 20 bins for the y-axis equals total of 400 bins. For a 20 meter long in 1D domain, I will get a 1 meter resolution for 20 bins, while for a 20 by 20 meters in 2D, I will need 400 bins to reach 1 meter square resolution. And if I want to stay within the same accuracy in a 3D scenario, I will need 8,000 bins or 20 bins cubed. If we are talking about drones or flying drones, this problem becomes even more complicated. From 3 dimensions, we can go to 6. The first are x, y, and z, and the next 3 are the attitude, roll, pitch, and yaw. Okay? So to get the position and attitude or orientation in 3D, we need 6 parameters. And if we want to add velocity at 3 different axes, the 6 becomes 9. So if we want to solve a localization problem for 9 dimensions using a histogram filter, the problem becomes much harder. Now, there are other filters, such as the Kalman filter, that are much more efficient in these problems, and we will meet them in the next sections. Now, with all due respect to navigating drones, I would like to come back to the 2-dimensional navigation and to introduce a new concept, orientation. In order to explain what orientation is, the best possible example will be a robot vacuum cleaner. Now, everyone that has a vacuum cleaner knows that it does 2 things, cleans and moves. But it moves in a very interesting way. It moves forward and backwards. And on top of that, it also spins on its axis to 2 directions, left and right. Meaning that at a certain point, the robot knows its position at x and y, but not any less important, it also knows its orientation or degree theta. Why does it matter? Because if the orientation is theta 0, for example, and if you move forward, you move to here. But if your orientation is theta 1, for example, and you move forward, you move over here. This means that the robot knows to interpret commands, move forwards, move backwards, and spin. Therefore, when we want to understand how this robot is built, or which parameters we must pass through, we enter 3 parameters, which is not only x and y, but x, y, and theta. These are the 3 parameters that we need to pass to the robot. If we want theta, for example, to be between 0 and 360 degrees, then we expand our space of possibilities. And again, since the complexity of the histogram filter is exponential, it becomes very challenging to solve this problem. And therefore, we come to another solution or another approach. And this is the Kalman filter. The Kalman filter doesn't take the region of interest and divide it into small bins. It does something completely different. And we will see exactly what the Kalman filter does in the next section. Good luck!